Hello everyone, we are Team Select from Tohoku University. Today, we present our research titled Aegis AI Optimized Space Elevator Architecture for Planetary Defense Missions. I am Yunosuke Kudo, and
I'm Masaho Yanaka. Let me begin with the background and the critical challenges we face. The space elevator is a massive transportation infrastructure. The apex anchor at the tip of the space elevator is expected to serve as a primary hub for interplanetary missions. However, this region is directly exposed to the harsh deep space environment. Here, we identify two fatal issues that put the system and humanity at risk. The first issue is the solar particle event. This phenomenon is a storm of high energy particles accompanying solar flares. High energy protons cause severe radiation damage to astronauts and sensitive electronics. The second issue is the collision risk of near Earth objects. Do you remember the Chelyabinsk meteor event in 2013? At the time, a small asteroid damaged buildings over a wide area. This event proved that even small objects can be catastrophic and the need for good defense measures. Therefore, we propose the comprehensive protection concept, Aegis. It integrates three core systems. First, shielding, protecting the habitat from intense radiation. Second, screening, AI-driven analysis and prioritization of asteroids. Third, interception, deflecting asteroids using the space elevator's unique mechanics. We want to explain these flaws in order. The first is the design of shielding against SPEs. We targeted one of the most extreme SPE in history, which occurred in August 1972. During this event, particles with an extremely high average energy rained down. To prevent this, we designed a hybrid defense wall combining an electromagnetic shield and a water shield. Specifically, we arranged superconducting coils to surround the cylindrical apex anchor, generating a powerful magnetic field. The Lorentz force generated by these coils bends the trajectory of charged particles, preventing direct hits on the living quarters. Furthermore, for high-energy particles that might slip through the magnetic field, we physically absorb them with a 1.2 meter thick water layer. Based on the NIST database, this thickness is calculated to be capable of stopping most particles effectively. To verify the validity of this design, we simulated structural characteristics and defense rates using 150 test particles. We succeeded in protecting 96% of particles. Since the energy of this penetrating component is weakened, we conclude that internal safety is maintained. However, this simulation revealed that magnetic holes exist at the top and bottom of the cylinder, where field lines converge. To overcome this, we devised an emergency leakage shutter mechanism. Under normal conditions, the shaft remains open for logistics and transport. However, in emergencies, it is filled with a layer of water to block radiation. This design allows the apex anchor to operate safely as a port. Next, Yunosuke will explain the second core system, screening.
thank you. To predict the risk of collision, it is important to calculate the minimum orbit intersection distance. However, its calculation cost is high. Therefore, we constructed a machine learning model that instantly predicts the noise. Therefore, we constructed a machine learning model that instantly predicts the void directly from orbital elements. In this study, we performed a comparative verification using four types of models: neural network, random forest, XGBoost, and linear regression. The neural network model achieved a high accuracy of approximately 0.9. This suggests the possibility of screening distances instantly without performing complex numerical integration. We also examined the classification of dangerous asteroids. To classify them, we investigated three machine learning models: random forest, light GPM, and logistics regression. The results of verification show that our light GPM model achieved an AUC of 0.95. The closer this indicator is to 1, the better the performance, confirming its utility as a screening system. After clarification, decision making on prioritization becomes important. The conventional Palermo scale is famous for measuring danger, but it fundamentally lacks the perspective of engineering feasibility for interception. Therefore, we propose the space elevator Palermo scale for engineering purposes. This scale introduces three penalty terms. First, delta velocity penalty. It is the energy cost needed for orbit change. Second, preparation penalty. It is the time needed until diffraction is ready. Third, uncertainty penalty. This accounts for the uncertainty of orbital data. The value of these weighting coefficients are dynamically set by AI, optimizing the strategy according to the value situations. This helps prioritization based on engineering feasibility. Finally, specific measures for interception. Rockets are limited in the mass they can send to space due to the structure weight problem. On the other hand, space elevator can utilize the enormous centrifugal force of Earth's rotation, creating a slingshot maneuver that ejects an impactor without consuming fuel. Inspired by NASA's successful DART mission, the deflect orbit, we verified how much deflection would occur over 10 years when ejecting a non-destructive impactor. Calculations determined that for a high-density tungsten sphere, a weight of up to 17.77 tons is safe. We simulated crashing this sphere against the Ophiuchus class asteroid. The results showed that the orbit could be changed by 7,000 kilometers after 10 years. Although this value exceeds the Earth's radius, a single shot results in only a barely successful avoidance. However, this is where the space elevator is important. Unlike rockets, where a single launch is expensive, the apex anchor allows for impactors to be ejected many times at low cost. The apex anchor allows for impactors to be ejected many times at low cost. Even if one impactor fails with the asteroid's orbit is unexpected, subsequent shots ensure mission success. This operation is the core advantage of slingshot. Another method for orbit diffraction is laser ablation. This method changes the orbit by irradiating a laser to evaporate surface material of asteroids. Irradiation from the ground is limited by atmosphere and the day-night cycle. However, the apex anchor, rotated in vacuum, can eliminate this limitation. Unlike ground-based system, there is no atmosphere to scatter the beam. This allows it to send thermal energy even at extreme distances. We simulated the diffraction distance with two patterns. This simulation shows that irradiation from the apex anchor had about 2.2 times capability compared to ground-based, generating a diffraction of approximately 74,000 kilometers. This demonstrates that the laser aberration from the apex anchor is better. It is important to use kinetic impactor and laser aberration properly. For example, the kinetic impactor is effective for asteroids with uniform high-density properties, and the laser aberration is effective for low-density fragile asteroids needed for long-term gentle thrust. In conclusion, AEGIS is a comprehensive system that integrates constant monitoring by AI, the base survivability by electromagnetic shielding, and much-layered interception by using impactors and lasers. This study has shown that the apex anchor can be the base of planetary defense. We are convinced that the space elevator will become a vital infrastructure not only for the transportation revolution, but also the security of the Earth and deep space. Thank you very much for your attention.